Now, there are techniques where you kind of exploit um, a concept called differential settling. Okay, and this concept of differential settling is typically used when you have mixture of particles of different sizes and different densities. Okay, so now in a method called sink and float method, what you do is somebody gives you a powder mixture and it has, say, particles of type A and type B, and say the density of the particle is rho A and density of the particle is rho B. Okay, now what I can do is I can put them in a column, okay, with a fluid, and if the density of the fluid that you're using, okay, if it is in between the density of the two particles that you have in the mixture, what will happen is one of the particles would sink and the other would float, right? So that's why, hence this name, the sink and float method. Okay, so in the sink and float method, what you have is a mixture of particles of different densities, and you use a fluid column whose density is in between the density of the two particles that you're considering, and then you basically separate it out. Okay, that's what is done in here. Okay, and there's a concept called equal settling. Okay, that's what we're going to do in the, okay, now, so in the different settling, what you do is, again, you have a mixture of two particles. Okay, maybe again, like say, okay, let me just okay, again you have particles A and B. Okay, and the density of the particle, as it is written here, is rho of particle B, sorry, particle A here. Okay, and this is rho of particle B, right? Now, what is done in the equal settling concept is that you basically use the fact that there's a difference in the terminal settling velocities between the particles of different densities. Okay, okay, I'm just going to, so what you do is, we know that this is the settling velocity for Stokes regime, right? And this is the settling velocity for, again, Stokes regime, but again for the particles of type B here, right? This is for type A and this is for type B. Now, if I say that the settling velocities of type A and type B are the same, okay, what I do is I can get a ratio of the particle diameters, right? Okay, what I do is rho T A is equal to rho T B, right? The density of the fluid is the same, that gets cancelled, right? Sorry, your viscosity is the same, your G gets cancelled. So basically, because of the fact that this and this is the same, I can actually get an expression for the ratio of the diameters as the ratio of the density differences, right? That's for the Stokes regime, and this is for the Newton's regime, right? Yeah, any questions? It's a simple fact that all I've done is I basically equated the settling velocities, right? Now, how this works, you can kind of understand, from from a diagram, okay, from a schematic. What you have here is, this is the terminal velocity, okay, and this is the particle size. Okay, now on the y-axis, sorry, on the x-axis, there are these vertical lines, right? These vertical lines here, right? So what you have is, you have a mixture of particles whose size varies from dp1 to dp4. Okay, I have two particles of type A and type B, and the size range of the particles in the mixture is the same. Okay, that goes from dp1 to dp4. Okay, now there's a horizontal line that is drawn here. Okay, and this horizontal line and this horizontal line, it corresponds to the equal settling, right? Because I'm just drawing a so this one, the plot that A is for is how the terminal velocity of the type A particle varies as a function of size. This is a plot for how the terminal velocity varies as a function of particle size for B type of particle, right? Now, what can I say about the size range from dp1 to dp2 of B type of particle? Just by looking at this plot, what can I say about the settling velocities of the particle size range from dp1 to dp2 for type B particles? Can I say that the type B type of particle in the size range from dp1 to dp2 settle, the slowest, right? Because any particle of type B from dp2 onwards settles faster, right? And all the particles of type A from dp1 all the way up to dp4 settle faster. Therefore, the size range of B from dp1 to dp2, that is, it settles slower than any particle of A type plus all the particles of B going from dp2 to dp4, right? Everyone agrees with that? So therefore, I can actually, what I can do is I have a column, okay, which is filled with a fluid. I introduce all the particles, at the surface of the, the fluid column, okay, and because I know that dp1 to dp2 of type B settles the slowest, okay, I can wait for the particles to settle for sufficiently long time, so that all the particles of type B from dp2 to dp4 settle, and all the particles of type A from dp1 to dp4 settle. Therefore, what you have in the fluid would be, what you have in the fluid that will be suspended would be only the particles of type B from dp1 to dp2. That's because they settle the slowest, right? So what can I say about this size? So now this is the, if I go vertically, that's the maximum settling velocity of, or that is the settling velocity of the largest size B type, right? Settling velocity of the largest size B type is this. If I move horizontally here, dp3, okay, dp3 of type A, dp3 of type A will have the same settling velocity as dp4 of type B. Therefore, the size range from dp3 to dp4, the size range from dp3 to dp4 will settle the fastest, right? So therefore, if I do experiments for a relatively short period of time, okay, I have a column, I introduce the particles at the surface of the fluid, okay. If I withdraw the fluid, so if I withdraw the particle from the sediment, okay, after an appropriate time, all the particles of type A from dp3 to dp4 would have settled to the bottom, and what you would have in the fluid would be all the particles of B from dp1 to dp4 and all the particles of A from dp1 to dp3, right? They will continue to remain in the fluid, okay. So therefore, what people do is people exploit this thing called differential settling, basically to separate out mixture of particles into different sizes, okay. And one thing I did not mention is that in this case, the density of the medium should be less than that of either of the substances, right? In the case of sink and float method, the density of the fluid is in between the density of the two particles, right? That's why one would sink and the other one would float. In this case, because you want both the particles to settle, and that will happen only if the density of the fluid is less than the density of the two particle mixtures, right? Yeah. What is that? Any answer for his question? So why are we not using sink and float method for this? Why are we thinking about equal settling concept? Why should we look for the density which is smaller than the density of the two particles that I have in the system? Any thoughts? Yeah. Yeah, that's one possible explanation. So what he's saying is that in the sink and float method, I would have to use particles, okay, of a fluid whose density is in between the two particles, right? However, if the density difference between the two particles itself is not too huge, okay, then you may have difficulties or challenges in terms of finding out a fluid whose density is between the two, okay. But the more uh, uh, I think it's because of the practical difficulties, okay. Okay, maybe there's an example here. So say that I have a two particles. Say A, there's something like a galena, which is one of the ores of one of the material, okay, whose specific gravity is 7.5. Okay, that means the density is 7500 kg per meter cube, right? Let's look at quartz. It has a specific gravity of 2.65. Okay, 2650 kg per meter cube is a density. Now you look at any fluid, okay, like say water, density is 1000. Okay, now go back and take a look at the list of fluids and the densities. It will be very difficult to really have a density which is more than 2.65. Okay, of course there are ways by which I can actually manipulate the density of the fluid. What people do is, I have like say water, I introduce salt, okay, depending upon the density of the salt that I'm dissolving. If I say like say I take NaCl, right, sodium chloride, okay, and I dissolve in water, what will happen to its density? It will go up, right? If the density of the salt that I'm putting in, if it is larger, then if it forms a homogeneous solution, the density will definitely go up. Okay, there are ways by which I can manipulate the density of the fluid, but however, for cases where the density of the particles are much larger, okay, than like say 1000 kg per meter cube, right? So it will be difficult to really find a fluid whose density is in between the density of the two fluids. Okay, therefore people do exploit this differential settling where the density of the fluid that you're using is less than the density of the two particles that you're considering the mixture. Okay. Okay, so now there's something called as a sharpness of separation. Okay, what I mean by that is, how given a mixture of particles of different sizes and different densities, how cleanly can I separate out the particles into pure fractions? Okay, what I mean by that is, okay, in the previous example, say I have a particle size going from dp1 to dp4. Okay, now I take this mixture, this has type A, type B, all the sizes from dp1 to dp4. If I'm able to separate them into pure A and pure B, okay, then my sharpness of separation is kind of 1, right? I'm able to separate them into two pure fractions of, okay, different population of particles, right? Now it turns out that the sharpness of separation can be improved if the density of the medium that I'm using is increased. Okay, so what I mean by that is, in the previous example, see, you had a specific gravity 2 and 2.65. Okay, if I use a fluid of see, I'm just going to make it as, okay, that's your density of the particle A and particle B. If the density of the fluid that I'm using is say 1000, then you'll get a certain fraction, like say maybe dp1 to say dp2, okay, as a pure fraction. Now if I increase the density of the fluid, okay, just to give numbers, let's say you're separating particles from 1 micrometer to say 10 micrometer of B into pure fraction. Okay, if I'm using a density of the fluid which is 1000. If I make it 1500, it turns out that I can actually increase the size range. Okay, I can maybe go from 1 micrometer to say 15 micrometer. Okay, because I'm able to get a larger size range into a pure fraction. Okay, it's a equivalent of saying, I basically increase the sharpness of separation is actually increased. Okay, so one of the ways of increasing the sharpness of separation is by using a medium whose density is by increasing the density of the medium in which you're using. The other way of doing this would be that if I have a way of choosing a size range which is closer. Okay, what I mean by that is, let's take this example. Okay, I've explained that by considering the fact that dp1 to dp4 is a size range that exists between that's for the particle A and B. I talked about the fact that this settles the slowest and this settles the fastest, right? For simplicity, let's say that I only have size range from dp3 to dp4. Okay, what I've done is, now I've done a closer spacing, right? Earlier I had size range going from dp1 to dp4. Now I have a mixture whose size range goes only from dp3 to dp4. If that is the case, I know that the size range dp3 to dp4 of A settles the fastest. That means I can actually separate out all the particles of A into pure fraction, and the fact that thus again the same size range dp3 to dp4 of B settles the slowest, I can also separate that into pure fraction, right? So therefore there are two ways of increasing the sharpness of separation. One is you use a fluid, okay, of a higher density, okay, or by increasing the density of the fluid, or other one is if you consider closer sizing of the feed. Okay, instead of taking a size range going from dp1 to dp4, you reduce the size range, okay, either going from dp to dp4 or dp to dp4. If you do reduce the if you have a closer spacing in the size, that will again give you another way of complete separation of the particle. Okay, yeah, okay. Correct. So why would you say that it will have some of A? Mm-hmm. Mm-hmm. Okay. No, that you would have to work it out. Okay, let me make another point which I did not make it. So in this differential settling method, okay, you can get a pure fraction of A and pure fraction of B, okay, and a mixture of A and B, right? That's what is a typical case. Okay, if you, when I talked about the size range going from dp1 to dp4, we saw that dp1 to dp2 of B was coming as pure fraction, and dp3 to dp4 of A was coming as pure fraction, and in between it was a mixed fraction. Okay, however, if you took this example of closer spacing, dp3 to dp4, okay, both A and B was coming as pure fraction, right? Now when you say that so the point that you want to make, you're saying that, so it turns out that when you use a density, so say that my size range is fixed, okay, say that I have a size from 1 micrometer to 1000 micrometer, that's the size range that I'm considering. Okay, so both the pure fractions that you get of A or B are kind of slightly expanded if you use, okay, we're going to have a question, a tutorial question, in the next class, wherein you're going to look at this example where we will see that if you use a density like say 1000 kg per meter cube, you look at what is the size range that comes as a pure fraction. Okay, now if you work with a fluid of higher density, you will see that there's an expansion, okay, or you get an expanded size range both in the A type as well as B type, and of course mixed fraction anyway is going to be there for both the fractions, unless you are actually at a particular sweet kind of a fraction where either you're working with a narrow size range or a particle of a particular fluid of a particular density. Okay, you will see that maybe in the next class. Okay, yeah. So the mixed fraction, that means the mixture of sizes are going to be there in both the cases, whether you use a fluid of a particular density or a higher density. Only thing that's going to be changing is the size range of the pure A and pure B that you're going to get by enhancing the density. Okay, any more questions? Anything that you want me to repeat a few things? Okay, so today's class we've kind of looked at applications of what we have learned, right? Both in terms of exploiting this in terms of doing some fundamental measurements in terms of measuring viscosities by exploiting the settling principles. We also looked at some applications where the settling principles are used in diagnosis. Okay, plus we also looked at a couple of examples where people use this motion of the fluid, particle in the fluid concept or the settling principles to separate out particles. If you have a mixture of particles of different sizes and different densities. Okay, we talked about sink and float method and the differential settling method for separation of particles. Okay, maybe with that we'll stop today. So far we have, when we looked at motion of particles in the fluid, we have always taken single particle, right? When we wrote this force balance, we took one particle and then we kind of identified the different forces. We did a force balance, we got the working equation, and then we got the expression for settling velocity, right? But that's going to be the case if you're looking at like say falling ball viscometer as a method for measuring viscosity, right? However, even if you go to this case, right, where you have a blood sample and you're really not dealing with one particle, right? In this case you have a very thin capillary. Okay, you have a blood sample and you have a large number of blood cells, right? So therefore you're going to talk about the collective behavior now, okay, in the next class, wherein we are going to look at cases where you have more than one particles in a fluid, and look at their settling behavior in the next class. Okay, so we'll stop today and then we'll meet up tomorrow here. Yeah, thanks.